Hi, everybody. This is Sean Lally, your instructor. I would like to chat with you a little bit about kinematics, that is, the physics of motion. Now, specifically, this unit we're talking about 1D, one-dimensional motion, motion in a straight line. So let's get to it. And I'm going to try and use maybe simplified versions of the equations that ideally will make these problems a little bit simpler. So first of all, let's remind ourselves, what is velocity? Well, velocity, represented by this symbol v, is very similar to speed. It is a vector quantity. What that means is that we not only indicate the magnitude, the size, the number, like 65 miles per hour, but we give the direction as well. So we might say 65 miles per hour north, maybe we'll say 65 miles per hour south, left, northeast, whatever, something like that. Now, the problem is that's generally not practical in equations, so we generally use a sign convention of plus and minus, and sometimes we'll use angles where needed. That's coming up in two-dimensional motion. So let's assume right now we're just dealing with one-dimensional motion, and the initial or primary or main direction of motion is usually what we call positive. So that can be up or down, it can be left or right. But generally, I suggest you always use the primary or main or initial direction of motion as positive, whether it's going left or right or up or down. And then let everything else be defined in terms of that. Okay, now the general equation for average velocity is displacement divided by time. Displacement isn't quite like distance. It is the straight line from start to finish. So it's often distance in one dimension. It's usually distance, but it is distance or displacement that is divided by time. And typically we use an x for x dimension divided by time. Now the units are going to be meters per second, although in imperial units it can be miles per hour. But in physics we generally use meters per second, sometimes kilometers per hour. Here's just a few speeds to keep in mind. Typical walking speeds are 1 to 2 meters per second. Running speeds are somewhere between 4 and 7 meters per second. That madman Usain Bolt can have average in the 100-meter dash, he averages 10 meters per second, if you can imagine that. By the way, 1 meters per second is about 2.25 miles per hour. So just keep in mind that Usain Bolt averages over 20 miles per hour. The man could be pulled over in a hospital zone. That's how fast he is. On the highway, car speeds typically about 30 meters per second. Professional baseball throwing speeds, 45 meters per second. You can read all these yourself, but these are just some sort of typical speeds that are worth keeping in mind. If you're wondering what a meter per second is, maybe this will give you just a little bit of context. Satellite speeds going around the Earth are about 6,200 meters per second. The escape velocity of the Earth, if you have had it on Earth and you just can't stand it anymore, the escape velocity of the Earth is about 11.2 kilometers per second, or about 7 miles per second. So start running fast if you want to leave the Earth. Here's my favorite speed. It's every physicist's favorite speed. It's the speed of light. It is a physical constant. It's approximately 300 million meters per second. There's no speed faster so far as we know. We use the letter c to represent it because c stands for constant and celeritas, which is Latin for speed. Constant celeritas, constant celerity. It's pretty hard to remember the actual speed. It's about 3 times 10 to the 8th meters per second, 300 million meters per second, approximately 186,000 miles per second. But it's also about 7 times around the Earth's equator in 1 second. So you could imagine a little bit of light traveling 7 times around the Earth's equator in 1 second, or going to the moon in about 1.25 seconds. Literally, if we aim radar at the moon, which we do, or we aim a laser at the moon, which we can, it comes back in about 2.5 seconds. And then light travels to and from the sun in about 8.33 minutes. That's crazy. If the sun were to shut off, we wouldn't know about it for 8.3 minutes. And in case you're wondering why we never can get anywhere in the universe, it's because our nearest star system, that's not the sun, the actual nearest star system is about 4.5 light years from us. That is, it takes light about 4.5 or so years to reach us from Alpha Centauri, a 3-star system. Madness, I know. This is kind of wonderful animation. This is how fast the speed of light is. Check this out. That's 7.5 times more or less around the Earth in 1 second. So this is a 4 second video clip and it's going about 30 times around the Earth, if you can imagine that. But wait, there's more. So this is a correct scale. The Earth here and the Moon over here. That's actually a correct distance and size scale. The Earth, if you let it be this size, the Moon is about 1/4 the diameter. To put it in terms that are a little easier to imagine, consider the Earth as a basketball, and that makes the Moon about the size of a baseball or a little bit larger. And now you have to imagine that they're separated by about 110 baseballs. So this will be in real time, sending a light pulse from the Earth to the Moon. Bing, pong. Wait, one more time. I love that. Now here's the best one. To go from Earth and Moon to Mars. Now this scale is right. The distance is right, but the actual sizes of the bodies have been increased by a factor of 20 so that you can see them on this scale. Otherwise you wouldn't. So these pictures are actually way too big. Okay, so watch this. So look how, I mean, this, you have to imagine the speed of light still moving at that crazy speed, but to go to Mars, which is almost twice as far away from the sun on average that the Earth is from the sun, it takes almost 3 minutes to get from the Earth to Mars. Now, of course, it depends on where they both are in their relative orbits around the sun, but still look at that. If you ever saw the movie The Martian, that's a central plot point that Matt Damon on Mars cannot have a real-time conversation with anybody on Earth. And of course, that's true anywhere you are in the solar system. You're not going to have a real-time conversation because it's too far away. So yeah, it takes light 3 minutes or so to get from the Earth to Mars. That's crazy. It can actually be longer too, and shorter under certain circumstances, depending on where the bodies are. This is at their closest approach, more or less. Okay, this is what I just said. Now I want to show you, I'm going to skip a couple of these slides because I think they're obvious, but I want to show you a couple of things. First of all, let's talk about instantaneous velocity. Instantaneous velocity is the speed you get in an instant, which is, for the most part, what you get from a speedometer. If any of you have had calculus before, you may have heard of derivatives. You might remember derivatives. And the idea behind an instantaneous speed is you take it's still distance divided by time, or x divided by t, but t is a very, very small time interval. So we could actually say it is a limit, or that we just simply make the time interval very, very small. You don't have to worry about calculus, of course, but I do think it's worthwhile to know that the instantaneous speed does presuppose a very tiny time interval, a so-called instant. And we can also talk about acceleration, which is the rate of change of velocity. It's how rapidly your speed changes. I do want to talk about acceleration for a moment. So with acceleration, it is how rapidly you change your speed per time. So what does that mean? Well, I want you to imagine being in a car and stepping on the gas and going from 0 to 10 miles per hour in 1 second. And then in the next second, you get yourself up to 20 miles per hour. And the next second, you get yourself up to 30 miles per hour, 40 miles per hour, and so on. The acceleration in that case would be 10 miles per hour per second. But that is a bit of a clunky unit. So in SI units, metric units, we use meters per second per second. You can actually use that as a meter per second squared, if you like, but I tend to think meter per second per second. So when we're calculating the acceleration, it is equal to the change in the velocity divided by the time. Again, don't worry about the calculus, but in case you're wondering what the instantaneous speed is, it's using a very small time interval. Again, it's the change in velocity divided by the time. Okay, let's get to the main event. The equations of motion. Here are the three definitions that we know. I guess I'm being a little sloppy here and I'm using a D instead of an X. I'm sorry about that, but maybe that's easier to use if you don't want to have to think about what does X mean. So D can also stand for displacement. So your average speed is equal to distance divided by time. The average speed is also equal to simply just adding the two, the initial velocity and the final velocity, and dividing by 2. And the acceleration is also, that's a mistake right there, by the way. It should not be an I. I'm just going to cover that up. Yeah. So it's the initial velocity plus the final velocity divided by 2. And the acceleration is equal to the change in velocity divided by time. And then you can do a little bit of algebra and come up with the equations of motion. And here they are. Oh, I switched back to x's. Man, I am being crazy. So these are the four equations of motion that are most often used. Final velocity equals initial velocity plus at. Distance, or x, equals 1/2 times initial velocity plus final velocity times t. X, or d, equals vit, that's initial velocity times time, plus 1/2 at squared. And then final velocity squared equals initial velocity squared plus 2ax. If any of you are gluttons for math and you want to see me derive these for you, just drop me an email. There is a fifth equation of motion right here, v final time minus 1/2 at squared, and it's great, but it's just not used all that often. Notice, by the way, that there's a variable missing from each of these equations. This guy's missing x, or d if you prefer. This one's missing a. This one happens to be missing final speed. This is missing time, and this one's missing initial speed. And I'm going to stop with that. So these are the guys right here. Now, if I were you, I think you should write these equations down in your notes. And you never have to memorize them, but you really want to have them handy. Okay, so final velocity equals initial velocity plus a times t, and all the rest of them. And by the way, if you're not sure what the variables represent, write that off to the side. Remember that VF is going to mean final velocity, which, by the way, does not have to mean final. It can just mean the final velocity in the problem or the final velocity in the step of a problem. And initial velocity doesn't have to mean initial. It could mean the initial once you start measuring. So I know it seems so tricky, and that's one of the things people hate about physics. It seems like we kind of change the rules and we throw so many equations at you. But I want you to find the versions of the equations that are most useful for you. I personally think these are the most useful versions, and don't be afraid to make that x a d if you would prefer. So that can be a d, that can be a d, and that can be a d. Okay? All right, I will talk to you soon.